So good morning, everyone. Today we are live with Ashish Ranjan Jha, who is currently at Revolt UK. He is building computer vision based KYC solution to automate customer onboarding, and we have a session on deep learning with PyTorch today and tomorrow. It is a two-part series certificate bootcamp, and both the series will be recorded sessions. So yeah, you'll get the recording sheet in a while. And I'll quickly hand it over to Ashish without wasting any times. And it is already 11:03. So yeah, over to you, Ashish.
Well, thank you, Ritu, for the introduction. So hello to everyone first of all, and thank you so much for joining. So this is a workshop, as you know, and two parts, right? So today is the first part, and I will quickly share my screen, walk you through what I am up to for today. So as Ritu mentioned, the name of the workshop is Deep Learning with PyTorch. So expect things about deep learning and things about PyTorch with an emphasis on PyTorch. And so just very quickly, what is inside today's agenda? First, I am going to quickly walk through this book that I wrote, which is the reason why I am here. This book called Mastering PyTorch, which is the book that I wrote about using PyTorch as a tool to apply for deep learning applications, build deep learning models, and put them into production. Then we will go and actually take some excerpts from this book. So I will use some exercises from this book and we will go through them in this session. So one of them is about building a deep convolutional neural network model using PyTorch, of course. And then there is this second exercise on using the concept of transfer learning. And once again, we will use PyTorch and we will try to learn, in real time how to use PyTorch to build such a system where we do some transfer learning, which is one of the disciplines within deep learning. And in the end, we will leave some time for you to ask questions and for me to answer if I can, hopefully. So without wasting much time, let's go straight into the first part about the book. So just for context for everyone, why did I write this book? Because there must be many more books about deep learning and PyTorch. So I don't know if you guys know about, firstly, if you guys know about Java, the programming language. I suppose you do. And within that, there is a book called Head First Java. Something very distinct about this book is that even someone who has nothing to do with computer science can still go ahead and read this book and make sense out of it, because it explains things with a lot of simple abstract concepts, very like graphic, simple, like cartoon characters. So it makes it very easy to digest and understand. So basically, having read this book, it occurred to me that within this world of AI, deep learning, machine learning, we have a lot of math which is daunting to many people, but it can be made simple. Like once you have worked in that industry for long, you understand that a lot of these things can be made more digestible. So that's where this idea came about. I wanted to make or write a rather hands-on book which people can learn concepts in and also apply them immediately right after. So that was my motivation, so to speak. And now I'm just going to quickly give a peek through the book and also tell which parts we are going to cover in this session. So this book basically has 14 chapters along 4 sections. So it begins with this overview, and first we go through the overview of deep learning, the basic concepts, layers, activation functions, and whatnot. Then we do a initial warm-up exercise where we build a image captioning model using CNN and LSTMs together. So this is a good way of grasping all of the actual concepts of PyTorch while building a model. Then the second section goes into a deep dive in the world of neural network architectures. So it's a good review of CNN, or like the vision models architectures. Then it goes through the recurrent model or the sequence model architectures like RNN, LSTMs. And also interestingly, towards the end, I try to cover some recent trends such as transformers, right, which have been replacing LSTMs and RNNs, as well as some rather interesting models such as the RAND wire NN, which tries to formulate its own architecture. We don't even need to provide an architecture. The third section is about generative models. So you might have heard about artistic AI, and we will cover one such exercise tomorrow. So this section is a lot about that, and also about deep reinforcement learning. So reinforcement learning is still in its nascent stages, I would say, with regards to coming alive in the industry. But you can still use PyTorch to make some meaningful applications or train some meaningful models using deep reinforcement learning. So in this book, I use the example of the video game Pong, and we do see like or demonstrate that our agent can be trained to beat the computer player in the game of Pong. Finally, this last chapter, which I have received a lot of uh, especially positive feedback about, is dedicated to PyTorch in production systems. So this covers a lot of things that classical textbooks would never cover. This is something from an eye of a machine learning engineer or a deep learning engineer who actually writes PyTorch code and deploys it in production. So what are the different hacks, what are the different standards to be followed, and what are the different tools such as or disciplines rather, like AutoML and explainable AI, and then using fast AI, for example, for rapid prototyping. So this section is more about the practical aspects or the real life tools that we can use alongside PyTorch for deploying such models. So once again, throughout the book, we have a lot of like elaborate graphics which walk you through the different phases. So in this the review of architectures, we go from all the way from the beginning of times of these models, and then we try to gather the perspective how we have come so far. And here you have the transformer model architecture, me trying to decompose it and make it easy to understand. And similarly for the generative models, this is a text generation model, which here we are basically seeing this beam search approach, which is, again, it can sound mathematically daunting, but it's not very easy. It's not very hard, sorry, to understand if we see it graphically. This is an example we will be covering tomorrow, which is about neural style transfer, which is a very fascinating example of what AI can do. But we will also see how easy in the end, like if we understand the fundamentals, easy it is to build such an app. And this is the game of Pong I was talking about using deep reinforcement learning. And finally, on the production deployment side, we have different kinds of hacks or different kinds of um, production tools that we can use to going all the way from distributed training to explainability, trying to see where is our model focusing on, or using fast AI to build a model, let's say in like 10 lines of code. So that's a peek to the book. As I mentioned, in this workshop, we are going to use exercises from chapter 3 and 4, as well as a specific example from chapter 7, the neural style transfer, tomorrow. So with that, the final thing is, obviously, this book is now available on Amazon or on Pact's own website. So feel free to check it out. And so from here, we can go actually to the one of the first exercises, which is about deep convolutional neural networks, unless there are any questions already. All right, I take the silence as a no. And so let's let's look at what we are going to do here. So I am assuming that you all might be aware with what convolutional neural networks are about. And we are talking about a vision model, which is to say that we will be using image data right now to train a model. And what kind of model will it be? It will be an image classifier. So imagine dog versus cat kind of an example. You have images of dogs and cats, and the model has to classify between those two classes. Now, the difference here is that we will have a multi-class classification task, which means that there will be more than two classes. We will have 10 classes. And we are going to use a very well-known data set, the Cipher 10 data set. The 10 stands for the number of classes. And you will see what kinds of classes it contains. So my goal here is to walk you through the entire life cycle of, like from the very beginning, importing libraries, setting up the model, like defining the model architecture, loading the data, creating the data loader, and so on, and then defining the model training loop, actually training the model, and then also looking at the model performance. So the model we will be using here is rather simple, with two convolutional layers and three subsequent fully connected layers. So that's the overall scheme of what we are going to do. And with that, we can get started with the first step. So whenever we are doing this exercise, think of these as the blueprints for how we try to go for the whole life cycle of building this model. So first up is always going to be, how do you define the model architecture? So this itself contains two parts. One is defining the architecture, meaning the different layers of the model, but also the forward pass functionality, which is forward pass is this technical term, which means if the input comes through to the model, how it is going to be processed at the different layers until the output is received at the other end. So these are the two functions, and I am going to show you, or I think I can still maintain this full screen and go back to one of the Jupyter notebooks where I am going to run this with you and explain you the different lines of code, hopefully within this time, these different steps. So firstly, we have a couple of libraries that you would install as you would do for any Pythonic task. So we have NumPy for any mathematical calculations. We have matplotlib just to plot some curves and so on. And then we have a host of PyTorch libraries. So Torch is the name of the parent library, right? We have something called Torch Vision. This is an auxiliary library, again built by PyTorch. This really helps us to swiftly get the data sets related to computer vision. So Cipher 10 is available through this API, and that's why we use this here. Then within Torch, we have the NN module, which stands for neural network, and it provides us all kinds of layers and functions. There is this functional API as well, and we will see how we use this in a bit. And within Torch Vision, we have this transforms API, which is used for performing all kinds of augmentations on images. As you might know, with images, we are used to performing augmentations such as flipping, rotating, clipping, and so on. So that's that. And finally, this is an important note as well, by the way. Always remember to set a seed to your experiments for reproducibility, so that if you run it again, you have the same result. So that's this line of code is for that, to set the manual seed. Okay, and from there, we come to the stage which I just mentioned in the slides, which is about building the model itself. And it contains of two steps. The first one is to initialize the architecture. And as I mentioned, this model, we need to contain two convolutional layers and three fully connected layers. So that is the declaration of these layers, right? And what are these parameters here? So as you can see in the comment right above, we mean to have three channels in the input image, RGB, right? So that's what the three stands for. And we want to have 6 output channels or feature maps. And that's the second parameter. And the third parameter is the n, or the n cross n kernel. So 5 is the size of the kernel I'm choosing, which will convolve around the image. And similarly, we have the second convolution layer with 6 input feature maps, 16 output feature maps, and 5 con kernels. Typically in CNN models, we try to increase the number of feature maps because it adds depth, and the spatial dimensions keep on reducing because of the convolutions. The second convolutional output then goes straight up to the fully connected layer, and you will see that the something called flattening happens, because now we are going from a 2D image all the way to a single 1D vector, and that's where we collapse all the 16 times 5 times 5 uh, pixels, let's say, into one dimensional vector, and which is followed by two more fully connected layers. So that's our model building, the architecture. And then we have the forward pass, which is rightly so represented by the method forward. And here we define exactly how an input X to the model goes through these different layers as well as the activation functions. So the as you will see, the flow is pretty intuitive, and that's where PyTorch really shines. The code is really easy to understand and helps you actually debug the entire flow very easily. So the input goes through the first convolutional layer, right? And then we also add this ReLU activation function. To add such activation functions is where the Torch functional API, which we imported here, comes handy and useful. So we do that and we follow it up with a max pool layer of 2 by 2, which is to reduce the dimension of the entire resulting image uh, by 2 times on both the x and y dimension. And we again pass it through the second convolutional layer, followed by a ReLU activation, followed by a max pool. So that's our convolutional part of the entire model. And here we do the flattening that I just spoke about from 2D to 1D vector. And we have a quick function here, which just makes sure that given a 2D representation of an image or a feature map, it tries to get all the dimensions except for the batch size and collapses. So this is a collapsing version. And so it collapses all the dimensions into one and then passes on and then basically reshapes, which is this dot view for reshapes that 2D vector into 1D, passes it through the fully connected layer number one, and the usual stuff, followed by activation, followed by second layer, followed by activation, and the last layer, which gives us the output. So this basically tells us how exactly the model is going to work as well. Once we have this entire class built with these two methods, we can basically start implementing
Hello, Ashish, we cannot hear you.
sorry, can you hear me now?
Yes, we can hear Ashish, but we lost your last 3 minutes.
Okay. I automatically got muted. Would you like me to repeat? And can someone tell me from where did you lose me?
Can you reshare your screen?
Yes. So let me go to the code again.
Yeah, it was around flattened feature.
Okay.
Fine.
I will repeat from there. Okay. Thanks. And if I got muted again, please let me know at the earliest. I don't mind. Thank you. So as I was saying, from these convolutional layers, we so imagine you get the 2D input image, right? So you perform the convolutions. Your output is still in the 2D format, but fully connected layers perform on the single dimension, because it's a linear layer. How do you do that? So that is where the process of flattening comes. And you will notice that in our definition of the first fully connected layer, what we do is we multiply the number of feature maps times the convolutional kernels as the input, and whatever be the output, that is okay, because that's one dimensional anyway. So this is um, this is the transition that happens between the convolutional and the fully connected layer basically. um, in the forward method, we declare everything. So initialization is basically about just defining what layers we want, but forward method is telling us how an input X, in this case an image, will go through these different layers up until we get the output. So we have our first convolutional layer, so we pass it the input and we get the output, and then we need some non-linear activation. The f or the torch dot functional .nn dot functional API provides us direct access to such activation functions. So I apply ReLU activation to the first convolutional layer output, and then I use a max pool layer again using the functional API with 2x pooling on both dimensions. And then
Ashish,
the
sorry to disturb you, but if you
hmm,
could just give some brief, like one-liners for every function that you have written, like you have FC1, FC2, FC3, then it is doing dot linear, or what is the meaning of prelude? Just one liners if you can give. And is I know that in this time it is like more to ask, but if you could do
Sure,
it
sure,
one.
sure. These are more than functions. These are attributes of this class, right? So we have a class, the DCNN model class, right? And what we are doing is we are defining the constructor of this class. So whenever someone calls this class here, it automatically assigns some attributes, and these attributes or properties are the layer names. So CN1 is convolutional layer 1, is short for convolutional layer 1. CN2 is convolutional layer number 2. And then similarly, we have fully connected layer 1, fully connected layer 2, and fully connected layer 3, or linear layers. Like these are the linear layers. And how we initialize them. So the torch.nn API gives us access to these kind of layers, right? So 2D convolutional layer, and we can specify the different arguments. You can go and read in the torch API documentation. It clearly specifies what argument means what. And here I have made it in this comment, made it clear that I want 3 channels as input. So the RGB image will have 3 channels, R, G, and B, 6 channels as output, and 5 by 5 convolutional kernel size. So that's how I initialize my different layers. So think of them as just 5 layers initialized for this model. And when we go for the forward method of this class, we start using this input, which will be fed in real time, which is an image, and we simulate how this input goes through the different layers and the different activation functions one by
Just
one.
just a quick question. So when you define the kernel size, or so how do
Mhm.
you come to this particular size? So like you want a 5 by 5 and you don't want any additional padding or something. So was there a thought given to that, or is it like just a simple
Yeah,
because it's a simple, right?
excellent question. So this is just a simple example. You can obviously play around with padding also of different types. You can try with different kernel sizes. All of that is a set of hyperparameters for us to play with for our own use cases. But this is just to show the simplest of examples.
No, could you please tell me, is padding necessary?
So it really depends. Padding, how the one thing that padding helps with is it maintains the same dimension across different convolutional layers. So if that is important to you, you could go ahead with padding because you don't want to lose the spatial dimensions of your input. But usually if you don't use padding, your kernel convolutional will also reduce the dimension, the spatial dimension of your input as we go along the convolutional layers. So it depends on use cases to use cases. For example, segmentation tasks, when you have to do some segmentation of different objects within the image, padding is kind of the standard. People do use padding, but for image classification, you are just trying to get the gist of the entire image. In that case, you can do away with padding as well. You can just try to reduce the dimension, flatten it into a single vector, and just get an understanding of whether it's a cat or a dog, something like that.
Irrespective of whether it is a grayscale or RGB.
Yeah, so that's it really depends again on your data and your model formulation. If your data has color images, it is always meaningful to use all the 3 channels because you have more information. But if you have grayscale images from the very beginning, you can't do much. So then you will have only one feature map or one channel in the input, and then you perform whatever you can with that one channel. So the
One more
padding
question. One
doesn't.
more question. Small question, please. Could you please give some insights now? So it is 3 by 3, 5 by 5 by 5, 7 by 7. Why it is 3 by 3? Why not 2 by 2 for RGB?
Yeah, that's also an excellent question. So technically, if you have a 3 by 3 or a 5 by 5, always try to think about how these filters are written. So they use odd numbers so as to have a overall zero sum of the entire kernel because it should not add any bias. That's number one. And number two, these kernels always, the way you operate them, a 3 by 3 kernel would reduce the dimensions by a factor of 2, which is an even number. So it's always more convenient to have odd number of kernel size which reduces the even number of pixels on each dimension when you go across different convolutional layers.
You mean to say adding bias is only to not to make the equation zero?
Yeah,
That is
so mathematically you would not want to add any like the sole purpose of these kernels is to find different kinds of gradients in the image, and their contribution in itself should not influence the image. They should learn what they can derive from the image. So if you think about the old school computer vision filters such as the Huff transform or those kind of old school filters, they always have a sum of zero, the overall mathematical sum, and this is where it more or less comes from. And by the way, no one stops us from using a 4x4 convolutional kernel as well, but as I said, this is more like a agreed upon heuristic standard that we use either 3x3 at the minimum, or we go with mostly the odd numbered kernel dimension size. But that's a really good question. Like, it's a good insight that you picked up on.
you mean to say it is a convention for RGB and grayscale 2x2, 3x3, something like?
No, so it has nothing to do with RGB and grayscale. Let's make that clear. RGB
Okay.
and grayscale is a different dimension altogether. It's a different discussion. Regardless of whether the image is RGB or grayscale, this kernel discussion is, as I mentioned, you more around why we have developed this, like why this kernel concept exists. So, like how we had the old filters, we developed from that to learn these filters. And as I told you, that there is a centroid of these kernels usually, and if you have an odd number like dimensions, then you will have one element at the center, which is the centroid, and it is easier to have a symmetry around that element across the kernel. So it's easier to get the gradients across that 5x5 or 3x3 kernel. For a 2x2 kernel, it's slightly more difficult because there is no central pixel in that or central element in that kernel. Okay, so I will move on. As I was mentioning, and also to keep track of time, um, the forward method basically walks us through these different layers and the activation functions. Essentially, it tells us how an input image X would eventually go through the different layers and activation functions and give us the output in the end. So with these two methods, we have basically our model. And when I was muted, I just ran this cell and I instantiated this model object. So we have one instance of DCNN model, and I printed it, which is allowed in PyTorch. It shows us all the layers with all of its different hyperparameters or dimensions, if you will. And this is exactly what we needed. So we have the first step done. And now we can move on to the second step in this life cycle of model building and training and testing, which is to define the model training routine. So what do I mean by model training routine? So I have this function here called train. Firstly, look at the different parameters or arguments to this model. One is the network or the model itself, the model object. Then there is something called a train loader. So this is a PyTorch data loader. It's an object which basically helps our entire training routine to fetch data from our dataset at every epoch. That's it. And we will then go into detail how it is being used or how it is defined. Then the third argument is the optimizer. And you might know that in all of these neural network trainings, we rely on the principle of gradient descent and backpropagation. So these the libraries such as PyTorch facilitate us to not have to think about these details. They provide us with these popular optimizers such as stochastic gradient descent optimizer (SGD), or the more famous ADAM optimizer, adaptive momentum optimizer. So it abstracts out the entire concept for us. We can just instantiate the optimizer and plug it in the system, and it will take care of the entire optimization process. Although I recommend for all of you to understand how the internals of these optimizers work. But again, that's the beauty of these libraries, that they enable you to just use the optimizers out of the box. And the fourth argument to this model training routine is the epoch. So which is basically how many epoch or which epoch number are you training this training routine for, because this function will be called in a model training loop. So let's say for I in range len 10, so 10 is the number of epochs, and then you call this training routine. So inside this training function, what happens is we basically need to get a loss function. We need to derive a loss metric. We initialize with 0 because initially nothing, there is no loss. And we then iterate through our entire data set, training data set. So for which we need to iterate through the training data loader, which gives us our data and which basically is decomposed into the input and the ground truth. Okay, so having the input and the ground truth for a given batch of our data, we can firstly initialize the optimizer. So dot zero grad means flushing off all the gradients from before. When I say from before, remember that this thing will be run in a loop. So there can be some remaining gradients from the previous run, but we don't want that to influence the current epoch. Then this is the step where we use our model object and supply the input to get the output. And this is exactly where our forward method will be called, if you are still following. With this output, right, and with the ground truth that we have from the batch of the data, we can compute the loss. In our case, we are using this cross entropy loss function, which is again directly available from the torch.nn API. So we calculate this loss, and with just one line of code, we can back propagate the gradients from this loss to the entire model. When we apply optim.step, this basically updates all of the parameters of the model using this backpropagation or the gradients that have been derived in the previous step. So literally these two lines of code does, I think, hundreds of lines of code equivalent of a job. So that's again a benefit of using a library like PyTorch. Finally, we are running this entire loop within this method, which goes through batches of data, right? So we need to keep track of the loss. So we add the current batch loss to the total loss within the data set. And we keep printing for every 1,000 batches of data, whatever the loss we have encountered. So this is a function that we have defined, and we will see this come into play once we are going to run this in the model training loop. Now, from the training routine to the testing routine, there is literally not much difference. The only difference is that for model testing, you just need to not do this back propagation, because testing does not mean you need to change the parameters of the model. You only need to run the forward pass. So this guy here, and then you get the predictions of the model. So the predictions originally come as a set of probabilities. So we have 10 classes, remember, in this image classification task. It's a basically 10 probability numbers for each image for each of the class. And this line basically finds us the class with the highest probability. So which is what we want, the prediction class. And we have two flags, the counter and the success flag, which basically keeps a track of how many images have we already evaluated, and out of those, how many are actually correctly classified. So that's literally the training, or sorry, the testing routine for the model. All right, so that's our second.
Can you just quickly tell me, like, so for optimizer and the net function that we have used, I understand like no grad. I mean, which were the libraries that you had mentioned at the top, like which corresponds to
Sure. Let's go through them once quickly. So the optim.zero grad, right? So the optimizer is something that we will feed to this function as an argument, and I am going to use that. So let's just for the sake of answering right now, this will come in the next steps, but we can use torch.optim API to directly instantiate an Adam optimizer, for example, right? Okay. And then with this optim, which is fed to this train method or train function, we can call the optim.zero grad. So that's all taken care of within the library. This net basically is the network, right? and in the line where we call this function, we provide DC and an object,
which is our function, right? Okay.
which is our actual entire
Initialize,
model, right?
Got it.
And so, as I mentioned, when you just call something in brackets to this object, this forward method is invoked, and it returns you, it passes the entire thing through all the layers and gives you the output.
Yeah, now it is very much clear.
Cool. Awesome. So as I was mentioning, we have done the two steps. First is to define the model architecture, the forward pass, and we have defined the training and testing routines. So the third step is we have not yet touched the data at all yet. And that's where we go to our data now. And let's look at this step by step. So first thing first, I would rather look at this line before the previous one. So Torch Vision API, as I mentioned in the first cell of this notebook, gives us access to popular computer vision datasets. So Cipher10 is one of them. So as soon as I call this line and I provide where I want to store this data, this will download the data for me with all of these arguments added to it. Now you will notice that there is another argument called train transform. So transform equals train transform. This tells this function, hey, don't only download this data set, but also apply some transformations to the data set. So these are the transformation steps that we have added. So if I show you quickly, in the Torch Vision, we imported something called a transforms API. This helps us to compose a set of augmentations or transformations to our images. As you will see, they are very easily understandable. So the horizontal flip is basically, yeah, it's self-explanatory. The random cropping is going to crop our image of at least 32 by 32 size and with a margin of 4 on each side. Then an important step is the data that is loaded is usually NumPy arrays, and we need to transform them into tensors because PyTorch will only work with tensors. And finally, as you all might know, in machine learning, it is always a good practice to normalize the dataset. So our input might be coming in pixel values such as 1 to 255 pixel values, which might not make sense to train a model in such a large range of input numbers. So it's always good to normalize your R, G, and B values. So these are the mean values that we want our image to have for R, G, and B channels, and these are the standard deviations that we want to have. That's the meaning of this line. All right, so we define
for creating our first model, we should always keep these normalized values as 0.5, and after running it once or twice, then we can change these values based on our input data set. Is it? Or it
so
always remains 0.5?
I would say this is a fairly standard practice to keep it at 0.5. One thing you can always do is you can analyze your data itself. If your data has a different distribution of pixels altogether, you might have to create some different kind of normalization. But for most cases, I can assure you that this works as a good start. And the 0.5 here is basically just average between 0 to 1, so as to keep the values within a bound and so that our optimizers do not struggle in finding the optimal value. You apply the same normalization to your test set as well, as you will see here. So you are always sure that when your model will be used for real time tests, they also go through the same transformation as seen here. So there is no risk. Your model will work as you expect them to work. It's just for the sake of optimizers to be able to perform easily. Because let's say if your image has ridiculously large pixel values like 255, for example, think about that as a number. In these equations that we have, the gradients might just blow up or down. So values such as these are always useful for optimizers to be able to find the optimal solution much more easily rather than oscillating a lot between high values.
How did
That's
you
the
came up?
main reason.
How did you came up with parameters for the random crop, like 32 by
Again,
4?
that's actually totally random. So it depends really on your image, how much you can clip. like how much do you afford to clip? I can give you a good example. So let's say you have images of credit cards or something like that, and you want to do something with that in different places in the image. You do not want to crop too much in that case, right? Because you might lose some part of the card in the image. So
Right.
these kind of parameters are again really dependent on the task you're solving. For our case, because our image itself is just 32 by 32, we did not want to lose too much of the information, and hence I'm just willing to crop maximum of 4 pixels on each dimension.
So, Ashish, can I say like whatever these parameter values we give to these functions, is it
Mhm.
like we can take some initial values, we can run our model, and we can always calibrate them to give better results, right?
For sure, for sure. Again, let me make it clear that all of these numbers that I'm writing here, like even in that model definition, consider them as hyperparameters. Consider them as something that you can play around with. You can write a grid search on all of these hyperparameters, and you can just run experiments after experiments to see which set of numbers gives you the best results. But this is just to initiate, like just to show how this example would work. There is no fixed rule that you have to use this. That's for sure. Cool. So as I told you, this
Just one
line
more
was
question, Ashish.
sure.
Sorry to interrupt. So, what is the logic behind using this horizontal flip? Means, why is it required? Generally, when should we do it?
Um, I could absolutely remove it from here. So there is also something called random vertical flip. So for this, I would recommend you to basically take a look on data augmentation for images. The goal is, so why are we doing any of these transformations? So think about it this way. We have this image classifier model that we are training on our data set. Now, in machine learning, what we always do is we test on some unseen data, right? Um, which is our test set in this case, which we will build here, sorry, here. But when we deploy this model in real scenario, the model might come across images which we might not have thought of before. So all of these efforts are to make the model as robust as possible to unforeseen scenarios. So let's say you have a model which you want to deploy on a drone camera, and let's say the model is on something, let's say a building detection model. So if there is a building in front of the drone, it does something, like it flashes light or something like that. Now what if it's raining on a certain day? Will the camera still be able to see the building with the same clarity as you trained the model on? So that is where you might want to augment your images. Might want to add some white noise, some rain noise. Actually there is also some augmentations available for that. So this is just to say that our models are susceptible to changes or augmentations in the image in real time. So we want to embrace this. We want to make our models ready for these unforeseen challenges. So that is why we use such kind of data augmentations. And there is a whole lot of such augmentations possible. Even a simpler example could be, what if your image is rotated slightly? Uh, if you did not add rotation as an augmentation in your model, then your model will fail. But if you added rotated images in your model as well during training, then your model knows how to deal with rotation.
So, why are we not using the vertical flip, like, or we can use
Obviously we can.
either
I
of
mean, if you want, I can just literally now add. So again, consider these as examples that I'm just trying to run across. But
Mhm.
you can obviously add a whole lot of transformations here. I'm actually going to add it here and just going to keep it because you mentioned it. So it doesn't matter. I just added them for examples, just to show
Uh,
you the abilities with torch.
guys, can we just go ahead with the the agenda for now, and then we'll take the Q&A after the session. So let's just not break the uh, just confirm on the chat, because I think it's little disturbing.
Ritu, it is, yeah,
The
it is okay.
doubt is more code related. So I mean that's why
I get it. You can directly post it on the chat box. We'll take it from there. Is it okay, Ashish?
Yeah, sure.
Because I think there is lot more to cover. and we don't have that much time left. So this is what I suggest.
All right. Okay. Yeah.
Just a quick question. Will this Jupyter notebook be shared with us?
Sure, I can share. Yeah, I mean, this is a part of the book, and I can arrange it via Ritu. We can share with you.
Okay.
Yeah.
Thank you.
Yeah. All right. So I'll move on. So similar to the training set, right? This is a training data set object. What we ultimately need is a loader object. The difference between a loader and a set is the loader is something like an iterator. So you can iterate on this loader to get batches of the data. So the only nuance or difference here is it takes train set as the input argument, but also the batch size so that you can run a for loop. So literally, like, I think we ran it somewhere, or if not, I will just show you how this will be used. So within the train method, I think, yes. So this is how we iterate on the training loader. It's like a loop on the loader, and the data is going to give us a batch of data, and the batch here is 8. So it will give us 8 images. That's literally it. So very similar to the training transform, we have the test transform. Obviously, for the test set, we do not apply these kind of augmentations because the test set is untouched. It should remain as it is. So we only apply the two basic transformations, which is the two tensor and the normalize, but not the random flipping and so on, because this is just to make the model robust during training, not during testing. And in very similar fashion, we derive the test set and the test loader. Finally, in the data set, just to make it very visually clear to everyone, I have enumerated all the 10 classes in order for the CIFAR 10 dataset. So these are the kind of classes that we will have, and we will see some of the predictions against our ground truth in one of the later slides. So yeah, very manually relatable examples basically. The final part of this dataset exploration was to be able to visualize a few samples. Let's go to that. So I have written a function called image show. Now this takes an image, which is a NumPy array. It basically unnormalizes the image because the images are normalized with 0.5 mean, and then converts into a NumPy array, and then finally plots it using the matplotlib library. So this is the function I will use now. But before I go there, I first need to get a sample or a batch of data. So remember, our batch size is 8. So on the train loader, this will give us 8. So this line basically will give us 8 images along with the labels. And now I will just run this to, okay, so we need to run this before, my apologies. And then we run this. So as you see, the images are fairly small size. So that's why you see them pixelated. But nonetheless, you have these 4 images, and then you have the underlying labels for these images. And this should also give you a peek into the task. The task is basically given an image like this, tell us whether it's a dog, a cat, a horse, a plane, or whatever of those 10 classes. This was our third step about the data set. We then come to the fourth and the second last step basically, which is to train the model.
Sir, very small question. Shall I ask you, sir?
Sure.
Very small, in fact. Supposing, let's say, example, now we do, divide the data set into train, test, validation. What I do in turn, I will take on synthetic data. It resembles the same. It resembles the same. So with respect to training and testing as well, I will take as a raw data or unseen data or aliens data. Is it possible to build my model towards my expectation?
So synthetic data usually should be applied only on training side, because unless your real-time performance also
I'm using for only training side only. Not on
yeah,
testing.
in that case you can use synthetic data. Yeah, the same flow can be applied literally. You can add more images of synthetic data to your training data set.
Okay, thank you.
Cool. Okay, so as I was saying, we will do these 2 steps. We will first run the model training loop, and we will go there in a bit. And finally, once we have our trained model, we will save the trained model at a given local path. So as I was telling while answering one of the queries before, The optimizer we can define it in one line of code. So it takes, it invokes the Adam optimizer. We provide all the model parameters. So the DCNN dot parameters is all the model parameters. And then we provide a learning rate. We can provide more things such as learning rate, scheduling, and so on. Please go and check the Torch documentation for these optimizers. It has everything you need. But basically, I'm using a simple setting with 0.001 learning rate. And just for the sake of keeping it quick, I'm even maybe going to keep it shorter than 5, let's say 2 epochs. So we train it for 2 epochs right now. Ideally, you should train for 100 epochs, let's say. In each epoch, we first call the train method, which trains the model, and we then call the test method. It's as simple as that. Doesn't get simpler. So let's run this. And while this is running, one quick note about the DCNN dot parameters. This basically tells you all the parameters that you have in the model, which includes the convolutional and the fully connected parameters. If you want to train on only a certain set of parameters, you can always go and choose DCNN dot CN1 dot CN2 dot FC1 and so on. So if I go back to the training loop,
just a quick question. So ideally, usually in production, so we will be it's more than likely we'll be using transfer learning, right? So like all these these parameters for available like model architectures, I mean they'll already be there, and then we'll be like mostly either using some part of it or not, right? So
yeah.
So like then just want to like printing it over here, like how exactly yeah, I mean, we can know more about like the underlying, the model or the architecture that we're using. Just can you just explain a little bit on this thing? Because
literally our next section is about transfer learning, so we will explore more there. We have one more exercise pending.
Okay, sure. Okay,
if that makes sense.
Yeah, that's fine.
Okay. So apparently it says test is not defined, so this should be now defined. Well, just to save time, as they do in cooking shows, I have one of the other notebooks ready with this whole thing run already for 5 epochs. So as you will see, let me walk you through what happens here. So remember our we have basically some 10,000 images in our test set, right? And so we go through these mini batches of data, and we compute the sorry, this is the train set, my bad. So this is the test set accuracy at the end of each epoch, and this is our train set with 50,000 images, and we have a batch size of 8. So that's why it ends roughly at the 6,000 mark, because it slightly exceeds the 48,000 mark here. So at every 1,000 images or 8,000 images rather, we show the results on our train set. What is the loss overall? As you see, the loss is decreasing, which is a good sign. The cross entropy loss that we defined. And when the epoch ends, we test our model so far on the 10,000 test images. As you will see, our accuracy on the test set is also getting better by the epochs. So over 5 epochs, it got to 60% for 10 classes. Remember, for 10 classes, a random classifier output would be 10% accuracy. So 60% is not too bad. Obviously, you need to train it for longer to get even better results. But again, we don't have time to do that. And I am just in this live notebook running it for 2 epochs just for demonstration. While we let that happen, I can already show you the next step, which is about saving the trained model. So you can specify a model path where you want to save your model. And then you can literally call the torch.save API, provide the model.stateDict basically gives us all the parameters, because that's ultimately what we need, the parameters of the model, and provide the model path, and then it saves us. Here in this model, we have our 250 kilobytes of model binary, which we will now shortly call in the next section. We will call this saved model and use it to make predictions. So that was the second part of the training and saving the model. So with this, we can actually go to the final section of this exercise, in which we first load this trained model, and we use this loaded model to make predictions on some test samples. So you can even do this in a separate notebook in another environment, because this binary is now with you. It is regardless of which environment you trained it in. So as I told you, we will save this here. And now for loading this model, we will do that here. So for that, you need to do two steps. First is you initialize an empty model of this kind, DCNN. I call it DCNN cached. And then I apply dot load state picked. And then I do torch dot load of this model path. So this firstly gives me all the parameters, and I plug all the parameters through this method to this empty model. So now my model contains all the parameters that I learned in my 2 epochs. Now, if I look above here, what I'm trying to do is I'm trying to load some test data sets to make predictions on. I have my images and counters here. And so I will be using again some image show the above method to display my predictions and so on. I will run the forward pass through these test images with the output. I will get the predictions with the maximum probability class, and I'll print them next to the images. So as you will see, we have these 4 images. These are the labels: cat, ship, plane, and the predictions are horse, ship. So it's basically 50% of the times correct. It is still learning. Basically, it is not there yet, as you also saw, because the accuracies are low. Once again, this is because we haven't trained it for enough number of epochs. So that's basically in a nutshell what we need to do. Like basically train it for 100, and I would encourage you all to do that in your spare time. Also change the hyperparameters of this model, and then you should be able to get go with this DCNN model on PyTorch. So yeah, that's it from this particular section. Now I don't know, Ritu, if we have time to be able to conduct polls or not. I suspect not, and because we already have had question and answers, it might make sense to go to transfer learning straight away, and then we can see if we have time in the end.
Okay, do you want me to launch the poll?
No, I'm saying I don't know if we will have enough time for that yet. So let's go through the session first, and then we will see.
Okay.
All right. So as one of one of you were asking, right, about transfer learning, and I do agree that in real life, that's what we mostly go for. We rarely train models from scratch. And so I really wanted to do this session also on transfer learning. So we will actually capitalize a lot on what we just did so far. So we will be using the same kind of task, which is image classification, but we won't be training a model from scratch. We will be using a pre-trained model. Okay. So I don't know if you guys have heard about the AlexNet CNN model. So this is the architecture. Instead of just having 2 conv layers, it has 5 convolutional layers and 3 fully connected layers. It's a very popular, like it was a groundbreaking moment in convolutional research. And we will be using this architecture pre-trained model on ImageNet dataset. ImageNet is also a very popular dataset with 1,000 classes. Okay. Now the catch is, we, on the other hand, let's say our company wants us to train a model on a data set called this one with just 2 classes instead of 1,000. So we don't have a pre-trained model for 2 classes, but we have this, and we don't want to train our own model from scratch. So how do we do that? And that's what this whole task is about. I will try to walk you through the entire steps, how to load this AlexNet model, how to edit it slightly, and then go ahead with fine tuning this model rather than training from scratch. Cool. So let's start with the process. Slight change of steps. So
Ashish, I'm so sorry to interrupt, but by the end of the session, can we like take 5 minutes out to take the questions and?
Yeah, sure. Yeah.
Okay. Cool. Thanks.
Okay. So first we will focus on the data set itself. As you will see, we first load our Hymenoptera data set, which has 2 classes, ants and bees. Very easy. And this should be familiar to you now. We need to transform this data set into tensors and normalize the data set. And we will also look at some sample of these images. So let's go to our code for this one. I have the basically steps to download the data set for you. Whenever you are going to use this notebook, simply click on this link, the .zip file. It should give you a zip folder, unzip it, and you should get this folder called Hymenoptera data folder. So the steps are here for you. This is basically important because this dataset does not exist as a standard torch vision dataset. So that's also one thing I wanted to demonstrate to you. What if we have our own data? So how do we use that? Still easy. It's not too hard. First, we need to specify the set of transformations that we apply to our data. So if you remember from the previous exercise, we have the horizontal flip. Here we have random resized crop. Uh, then we have the two tensor and the normalized values. If you ask me, Ashish, why are these values different now? This is coming from the data set because this was the mean and standard deviation of pixels across this entire set of images in this data set. So that's where these numbers are precisely coming from for the training and validation set. Once we have the transformations defined, we can firstly we need to fetch the data. So I do this in the dictionary format for both training and validation at once. So if you are confused, just think of this as train and think of K as train for everything. So first up, we need to specify the training dataset object. So it basically looks for this directory, joins with train, which is basically to tell you that this has a train directory with ands and b's directories, and all of them have images inside. So that's like pretty straightforward, no magic there. So we create this dataset object out of it using the dataset.image folder API. Image folder means you just need to provide what folder has the images with the class names ands and b's. And we do that for both train and val in this line. Then if you remember from dataset object, we need to get to the data loader object, which basically means we need to create an iterator with a batch size. So we do that for a batch size of 8 with these objects, the above dataset objects. And this is just to compute the length of the dataset size. This will come in handy if you need to check how many images you have in train and validation. And then this image data train.classes tells us how many number of classes we have. This is again basically telling us how many folders this folder has, which is 2, which is the number of classes. And finally, this is something wanted to show you as well. Like right now, I'm obviously working on showing you things on my MacBook, so I don't have a CUDA or a GPU available, but you can always work these exercises on all kinds of hardware. So if you have CUDA available, you can use GPUs to run these model trainings even faster by this line of code. Cool. So we have defined our data set and data loader objects here. Now, the last step here is to also visualize a few samples. Once again, we have a similar kind of a method for image show. We unnormalize the image once again by basically multiplying and adding instead of dividing and subtracting the average and the standard deviation. And then we convert it into a NumPy array and just show it as an image. This line gives us the next batch of training data set with the images and the class ant or b. And then we create an image grid. So you will see this here. If I only ran this one first. Okay, so basically you are seeing a batch of 8 images and you are seeing all of them are either ands or b. So the images and the respective classes for them. I hope that is visible and clear to everyone. Cool. With that, we have covered the dataset aspect of this exercise. Now we are going to the most interesting part. So in transfer learning, what we need to do is we need to get a pre-trained model. We are lazy. We don't want to train our own model from scratch. Okay, fair enough. Torch Vision API, besides giving us data sets such as Cipher10, transformation functions ready to use, also provides us models, well-known popular models, such as AlexNet. So that is where I call this models. So torchvision.models.alexnet, and I provide this argument pre-train equals true. This means it will not just provide me the architecture of the model, it will give me the model with the pre-trained weights on ImageNet dataset. If I run this and I print the model that I have just loaded, it gives me the AlexNet model. Now the model itself has two parts, the feature extraction part and the classification part. And the feature extraction, as we saw in the diagram before, is basically the convolutional part, which with 5 convolutional layers. The classification aspect is just the 3 fully connected layers thereafter. It is very similar to our previous model, which had 2 convolutional layers and 3 fully connected layers, but this time we have slightly more convolutional layers here.
Just a
But the
quick
most
question.
important,
Just a quick question. So, can we do any customization over here to this, or is it going to be like preloaded itself, or are there versions of LXNet, different versions of LXNet model that will be available? Like, let's say we have the dropout rate, which is more of a, well, uh, I mean, I'm forgetting the term. I mean, this is like more used to kind of for dimensionality reduction or whatever it is.
yeah,
Like, yeah. So
regularization.
regularization mostly. So P is equal to 0.5. Can we change these, or are there other versions of these models available?
Um, I can check this for you literally right now. So if you do torch vision models, this will land you to a page, right? And this tells you for different models, such as for AlexNet. So this takes us to the paper itself. So you will have the APIs for each of those, and hopefully they also have, yeah. So this one tells you that they have this pre-trained model. I think unfortunately for AlexNet, they have this particular one only, and I can explain you why. So this is basically to tell they are giving us the model that was published in the paper of AlexNet, right? So it's not really that the authors of the paper trained multiple different versions of the model. They trained the one model which became successful and popular. So
Right.
they gave us this model. You can always change parts of it, but then you will also lose the weights if you change parts, if you know what I mean.
Right.
So if you remove a layer in between, you will lose the weights between this layer and this layer and this layer and this layer. So I can show you. I was just getting on to the next section, which is you can use this model object and you can call the different attributes like feature dot classifier to explore these different parts. So the dot feature part shows you the convolutional part. You can even go and just look at the first layer, and then you can even do, I'm not going to do that right now, but you can do something like, hey, I have gone mad, I'm just going to change it to a linear layer now. So you can even apply changes like this and just literally. So let me show you. It might not work for now. So if I do this right, let me now print the model for you. This is hypothetical. This does not make sense, but you will see now that we have edited the model,
Okay.
if you see what I mean. Cool. So but let's again load the fully preloaded model and continue with the discussion.
Okay. Got it. Yep. Thanks for showing this.
No worries. So we have our AlexNet model, and now, as you were asking, right, we need to make one change for sure in this model, which is the final output layer of this model has 1,000 classes, but our poor data set has only 2 classes, B's and Ants. So that is where we will make a small change. We will access the dot classifier and then the 6th or the 7th layer rather. So this index number 6, and we will change it to a linear model with input 4096. So that remains the same, but the output becomes the length of our classes, which is 2. So this is how we change. So let me run this and let's once again print the entire model. And now you will see at the end, you have, instead of 1,000, you have 2. So this is the essence of this exercise. We have loaded a pre-trained model. So all of this remains the same. All of our weights here remain the same. The only thing now which is empty or which we need to train is the last layer. So these weights are gone because this was a different matrix. Now we only need to train this one, and these we already have from before, a nice pre-trained set of weights. So with that step done, which is I think the most important step of this exercise, we can go to the further steps. So We will now define the what we call the transfer learning routine. You can call this a model training or the model fine tuning routine. Sorry, is there a question? Okay. So, and with this routine in place, we can code the training and validation, pardon the misspell here, of the pre-trained AlexNet model on our dataset. So let's go on with that. If you remember the defining of the training method in the previous exercise, this is very similar, but it's called fine tuning because we are not training it from scratch. Now this once again takes in 4 arguments. It has the pre-trained model object, which in this case will be our model fine-tune object. The loss function, which we will define. Typically, it will be binary cross entropy loss for binary classification tasks like this one. Optimizer, let's say Adam optimizer, and then the number of epochs. So in this entire function, we have this model training loop, which goes through the number of epochs. Now, you will notice that we copy the entire set of the entire weights from the pre-trained model, the AlexNet model, in the model weights. Just keeping that in mind. And we begin with an accuracy of 0 from the beginning of epochs, and we will add to this accuracy as we go along. Okay, so within this training loop or model fine-tuning loop, within this model fine-tuning loop, we iterate through the training and validation set. First training and then validation, obviously. So if the data set is training, we set the model to training mode. This is important. This is to tell the model that, hey, please allow your parameters to be updated, because in training mode, we want to apply back propagation. But if we are running the model in validation mode, we run this .eval, which is to tell the model, hey, do not change your parameters, do not apply back propagation, only allow forward pass for evaluation of the model, not for any training of the model. And so once we have gone through this, right, we have set the mode for the model accordingly. We do the similar stuff as before. We go through the batches of data. Each batch gives us images and the labels, images and targets to be precise. We use this .to device. If you remember, I told you if you have GPUs, you can apply the same like training routine on a GPU device. So this basically line places these two tensors on the GPU, because this is an important step. The GPU should know that I have to, allocate some memory for these tensors. In my case, this will be CPU, so nothing special. Then we flush off all the gradients for this current epoch if there are any outstanding gradients from the previous epoch for the optimizer. And here you will see the classic training process, which is we run the forward pass here. So it goes through the entire AlexNet model all the way to the last two classes probabilities. It gets the maximum probability for like whichever class has the maximum probability, it gets the index for that. And then we compute the loss using the loss function. So imagine this to be a binary cross entropy loss function. So you have the output probabilities, and then you have the actual ANDs or B's target, and you compute the loss. Finally, if you are working on the training mode, you apply the back propagation, and then you update the gradients of the model. Once you have done this for either of the data set, you add the losses basically across the entire batch. So this is one batch, right? So this loop is running through batches. You keep adding the loss batch by batch. And also you keep track of how many of your predictions are successful. At the end of this entire batch of like entire data set, basically, you compute what is the loss divided by the dataset size, because to normalize the loss, if you have 10,000 images, you don't want your losses to keep on adding and multiply to 10,000. So you divide and normalize your loss. And similarly, you normalize your accuracy. So very similar to the previous exercise, you want to log your progress as you go along the epoch. So we always keep logging, hey, the loss in this epoch is this, and the accuracy in this epoch is this. So that's that. And one final thing, how do you checkpoint your model? So the logic is written here clearly. We maintain this accuracy. We initialize with 0, right? And we compute the accuracy at each epoch. if our accuracy at this epoch is bigger than the best accuracy seen so far, then we set the accuracy, the best accuracy seen so far to the current epoch's accuracy, and we then save like these model weights, these best model weights seen so far in our model weights variable, because in the end we will be loading the pre-trained model with these model weights, because that's the model we want, the model which had the best validation set performance, which is pretty straightforward in any machine learning task. Once we have done this entire training loop and logged everything, we return the pre-trained model once again with the most optimal model weights. Okay, cool. Now the second step is basically very simple. Just to be able to use this define fine-tuning routine. So as I told you, we will be using a cross entropy loss. In this case, it will be essentially binary cross entropy loss because we have only two classes. And we will be defining stochastic gradient descent as an optimizer. If someone of you might ask, hey Ashish, why you used Adam before an SGD now? Please remember, this is again just for example purpose. Feel free to play around with the optimizer, and if you run one of these, you will get a sense of what you want to use next. If SGD is too slow for you, you might want to try Adam. But if Adam is too noisy for you, you might want to go back to either RMS prop or SGD. So this is just for example. Once we have defined the optimizer and the loss function, you have everything to plug in to this method basically, which I am going to call it here now. Again, I need to first run the previous cell. And when I call this for a total of 4 epochs, it starts logging things. It's going through the first epoch now. Once again, like a cooking show, to keep things in speed. I have run this from before on a different notebook. Let me show you how things are running inside. So at each epoch, we register the training loss, which is basically the log loss, right? And the accuracy. So accuracy is 50.4%, let's say, at the first epoch. And similarly, the validation loss and the validation accuracy. If you keep going down these epochs, you will notice that the losses for both training and validation are decreasing from the previous epochs, and the accuracy for both training and validation are increasing from the previous epochs. In the final epoch, we have 87.6% accuracy and 81.5% accuracy for validation and training sets respectively, which is not too bad for a binary classification task. And the losses are still going down. Obviously, goes without saying, this is only trained for 4 epochs only for the sake of time. I would encourage you to train it for much longer, and I am quite sure that the performance will go much further up and perhaps reach like 99% or maybe even more accuracy. This is also to show you one more thing, which is transfer learning is so useful in that way. It can accelerate your learning very quickly. So in just a matter of 4 epochs, you have gone from initial accuracy of 66% on validation set to 88% almost at the end of 4th epoch. This is because you have a lot of pre-trained parameters suitable to an image classification task. And this is what we usually do in real life as well. We try to leverage what we have already as existing models, not trying to train from scratch, basically. Okay, so this while this is still training, we can still go to the next step, which is well, we already ran this. So we defined the loss function, we defined the optimizer for the model training, this being the cross entropy function, this being the SGD, the stochastic gradient descent optimizer. And finally, we ran the model training loop. We saw the logs, and I explained you what these mean and how transfer learning is helpful in getting us to very high accuracy in a very small number of epochs. This is the first step of our exercise, which is to visualize predictions from the trained model. So first we will define a function which will take in some samples from test dataset and the model object and give us some visualizations. And we will use this function then to observe the visualizations itself. So let me walk you through this function first. It takes in the pre-trained model object, which is important for making predictions. And then it also takes in a parameter which says how many images you want to visualize for predictions. So here I set the seed to 1. This is again for reproducibility, so that if I run this function again and again, we see the same 4 images and we can reproduce the results. Okay, so we have this pre-trained model dot training as was model training, right? And we have this pre-trained model dot eval. So this basically ensures that our model is set to the evaluation mode, because here we don't want to change parameters of the model at all, right? And these are all the details from the matplotlib library to basically plot the image. Once we have done all of that under a no grad context, this is also important to let PyTorch know that we are not playing around with the parameters or changing the parameters. We iterate through our tests, or the validation set in this case, of a batch of validation set with all the images and labels. We set them to our device, which is CPU in my case. We run the forward pass. We get the predictions, the maximum prediction class for each of these images. And then we just basically do the thing of printing the class predictions against the actual ground truth, and also showing the images for each of them. So once again, I can show you here in this example. If we run the above function, we get these 4 images and we get the predictions and the targets. So as you will notice, it is performing correctly on 3 out of 4 occasions, so like a 75% accuracy. It is getting one of these images wrong, which arguably could be a difficult one to catch as well. If you trained it for longer, if you trained it with different sets of hyperparameters with more augmentation and whatnot, you might be able to get better performance. But I leave it for you to try to beat the performance I'm showing you here right now, and try to play around with both this model as well as the previous one that we saw on training a model from ourselves from scratch. So I think that's basically it. And yeah, just running it live right now for you to see again. There you go. So basically, that's pretty much it from my side. And then we can basically move on to Q&As. Over to you, Ritu.
Okay, do you want me to pick out the questions for you?
Sure. Yeah, that would work.
Okay. Okay,
Or
so
if I can read from somewhere, like that's fine with me as well.
yeah, totally. We can pick
What
out the
if we
questions.
ask them like orally?
Sorry.
If we can ask them like right now rather than writing, because what happens there, once you write a query, you have some subsequent question over that. So just posting one question does not answer completely.
I will leave it for you guys to figure. So I am fine with both formats. Let's go with the questions.
Can you please explain this? What exactly is the ground truth? Where will like IM and ground
Okay. Okay. Ground truth basically always means what is the actual label for the data. So it's label. The keyword you can think about is label. There are many words for it. So you can say target, you can say label, or you can say ground truth. All of them mean the same thing.
Okay, so Ashish, what happens in the production grade environment? Suppose we have created some model and in our
Mhm.
development, okay, but when our model is being used in the production, like you have the Google Lens, right, where it must be using some kind of uh, modeling or whether it
Mhm.
is TensorFlow or Python or something else. But I want to know the how do we do that? Like writing a code on a Jupyter notebook is fine, but how does it happen in the production? Like how do we create model and post it, and then it is being used for how it is getting the images at runtime? Because there may not be a single place where all the images are present. There may be a lot of paths given. So it is
Okay.
using all those images to do the
Sure.
training.
Sure. So firstly, a lot of that is really out of scope of what we discussed. First thing, not to like plug my own thing here, but genuinely, I feel if you refer to like when I was talking to you about my book, uh, the last section of the book itself. So if I go to this section, the PyTorch and production systems, literally walks us through all of these things. So when you're talking about how do you actually make it into an app, either in mobile or as a service in the cloud. So a lot of that has to do with also machine learning engineering. You need to know about microservices. You need to. So we touched briefly, by the way, one aspect of it. So if you remember that we saved a model binary here, right? That's the starting point. We need to be able to at least have a model binary with us, which we did. And imagine this cell, but in a much bigger way. What we are doing here is we are loading a saved model and then making predictions. We need to do this, but in a much more elaborate fashion. We need to write microservices around it. We need to still load the model there in this fashion and run predictions in this fashion. But there is a whole lot of work that goes around putting this system into production. What that means, where are you trying to place it in the cloud? What is the use case? Is it latency driven? Do you need it to be fast? So how many models you need to spawn together? Then there is something about model versioning. So I think it's a very huge topic, to be honest. And the one of the things I recommend is to really go through the section 4 of the book if you have it already, or you can also like basically Google all of these things. You can learn on yourself, but it's very difficult to cover all of that in one, like, Q&A session of this presentation.
I
So
understand. Yeah.
does
Thank
your
you.
section 4 covers everything, such as like over here we have saved the model locally, but let's say on a cloud, on a remote server, how we're going to save it? And then you said like spawning multiple models, like how exactly we're going to use, depending on the kind of machine and depending on the kind of input and output data size that we are looking at. So how exactly we are going to design our like how to run machines parallelly. It talks about all those things, and how exactly then of course we're going to put our model on a Git version where we also can apply
Yeah.
CI/CD so that we can automate the entire process. So does it talks about
Yeah.
everything? Okay.
Yeah, so that basically would mean, I mean, firstly, again, to manage expectations, the tomorrow's part is also not going to cover those aspects too much in detail, because I think that requires a workshop of maybe like 10 hours to really go into depth of deploying the model and making all of those things, decisions, CI/CD, creating a model service, a model server. So we can have, like, I can talk to Ritu and others at UpGrad. We can have a separate session around just the production systems, which will also need much more preparation than just running notebooks. Yeah, but again, I will resort to
Do
the
you
current
provide
best answer
do
that
you
I have.
provide sessions yourself? Like if some of
No,
our
not at the moment.
okay.
Yeah, that'll be great. I mean, if you can have
If you can have some sessions, like if
Thank you.
we have to do something extra for that, that is also fine. But if you can walk us through all that, if some
Okay,
of the
the point
background.
noted, and I hope Ritu is also making notes. Yeah, cool. Any
Ashish,
other questions?
Ashish, this is Aman. I have one question. Uh, See, my question is regarding the transfer learning. Now,
Okay.
suppose we are doing an image classification or image segmentation, and we extracted the high level features and learned through the transfer learning. But the lower level features we want to change it because we need to extract the lower level features, and these may not be there in the pre-trained model or the model which we are. So in that case, what is going to happen that some of the weights which are uh, already learned, so we don't want to change some of them, and we want to change some of the probably the lower level features, and the weights will be changed accordingly. So how to deal with those type of the transfer learning problems?
Sure. So on the technical side, as I was demonstrating while doing this exercise, it's always possible to just edit what you are saying. If I understood you correctly, you want to change the lower level features. So essentially, you want to create a new feature extraction process, but you want to retain the classifier, the higher level features in this way. So the only thing is literally to change this, the feature set here. It will create a brand new like empty set of parameters for all of these layers, right? But then all of the parameters in this part will remain intact. It will obviously take much longer to train them because the training, the back propagation or the gradient computation starts from this, right? So if you have empty or like randomly initialized convolutional layers, it will take longer to train. But as you said, if you must train your own lower level features, then yeah, then we go for it. And I have done that myself for some cases as well. So you have a, let's say, an image segmentation tasks for, let's say, real time, urban landscape segmentation, but you want to use that model for segmentation of a totally different kind of an image, let's say an ID document, and you want to classify faces, text, and everything. That's a very different use case. So in that case, I would recommend to basically here you just, instead of having this, you start defining your own sequential and whatever you want to have. So I mean, you get what I mean, right? Like, just for this example, whatever. I mean, you get my point, right? So you
Yeah, I
basically
got your point, Ashish.
Mhm.
Do you have any pre-trained, probably any notebook regarding that, where you have changed some of the features? So because it will give a better idea. If you have, then probably if you can can you
So
please share it?
how do you mean pre-trained notebook in that sense?
Uh, where you have changed extracted the higher level features, and then as you are saying that you have done it earlier. So if you have
Yeah, so
any
Amar, that is part of my work. So I'm really not
okay.
sure if this is more like an experience I'm sharing, not something that I, independently worked on. But this is something as an experience I have worked on in my current work at Revolut. But I'm just saying that this is, all of these combinations are possible. Just know that whenever you edit something in the model, the thing that you lose is the trained weights, because as soon as the dimensions change, you can't use the same weight matrix from as from before. So that's the trade-off you need to always work with.
Ashish,
Okay.
can you give some session on AWS EMR, where you have most of the things prepared and you just have to, like, you can implement the CI/CD or very easily there. But I do not have the complete idea of that. I have read about it, tried to do something, but I was stuck in multiple points. So if you have like idea on EMR, because it will be easy for you to give insights. And
Sure.
if
Yeah, I mean, we can work this out. I don't know if UpGrad will be interested in this. So yeah, because you guys are raising a lot about this ML engineering part of it. Yeah, maybe I will take this forward with the team to have a subsequent session on this.
So that kind of helps because it kind of clarifies the entire picture and definitely helps you feel more confident in your work, because I think most of the time, I mean, that's exactly what you're doing. I mean, they were doing model fine tuning or something at the end of the day, but then that's exactly most of the time that you kind of struggle with a little bit, and it's hard to learn on your own until unless, because I mean these kind of things require like GPUs and multiple, I mean the power that is required, so it's like very hard to learn on your own. I mean you can get the theoretical part of it, but even if you can get someone like actually doing it in person, I mean that still helps
I agree.
helps
Yeah,
the
yeah,
growth.
makes sense, makes sense. But yeah, again, this needs a bigger time frame. Firstly, I don't think it can be done like 1 hour as well, and also this needs a lot of preparation. So let me discuss that with your, like, with the UpGrad team. So, and if we can come up with such a thing, I see a lot of appetite in you guys, and that's really heartwarming as well that you guys want to learn that. Which is, I agree, it's one of the most important things, one of the most important gaps between where you are right now and where you want to be. Once again, guys, not to advertise or anything, I'm just telling, I have put a lot of effort in this like fourth part of the book, so this covers a lot. In case we have some time from now to get the workshop done, you can refer to that fourth part of the book. It contains a lot of insights into model deployment.
I mean,
is
sorry
it
to ask that. I mean, what's the cost of your work?
um I would not know as of now, but it goes through a lot of discounts and so on. So this book is launched as part of like in this UpGrad workshop thing, So you can check with Ritu, I suppose, about the exact prices. It should be discounted for this promotion.
Okay.
Okay. Yeah. Ritu, please share a link or whatever it is. I want to buy this book.
I'll get the links
Thank you,
from
Ritu.
Ashish, and yeah, we'll
The
share it with you
discount,
guys.
of course.
Hi, Ashish.
All right.
I have a question.
Sure, go ahead.
I want to get a deeper understanding of PyTorch, especially working with tensors and performing matrix operations, working with gradients and all. So do you still recommend your book for that, or is there any advanced level PyTorch book to learn those concepts well?
So if you want to forget about PyTorch, when you mentioned about matrices and tensors, there are some really good classical deep learning books. So there is this deep learning book by Ian Goodfellow. If you really want to understand the fundamentals, I highly recommend that, because the way you framed your question, it sounded like you want to go into the fundamentals really. And then if you want to use PyTorch itself as a tool to do all of that, then I mean, again, I don't want to sound like I'm boasting, but you can use the book I have written, or you can also think about deep learning with PyTorch. I think there is one more book around PyTorch. I'm not sure if it is specifically on deep learning applications, uh, under Manning publication. So I mean, I'm always open for the best option out there. But from the way you asked your question, deep learning by Ian Goodfellow could be a great resource for you to look into the fundamentals.
Thank you.
All right, so maybe I can take
Hi.
one last one, Ritu.
Hi. Hello.
Hi, yeah, I can
Yeah.
hear you.
This is Sharath. I just want to understand can you throw some light on NN module, NN dot module, and the first line that after the init function you're doing, not in this notebook, the previous notebook.
Okay, the previous one. So here.
Yeah. Yeah. The NN module. You're you're taking the super class, right? NN
Oh
module.
yeah, oh yeah, oh yeah. Okay, yeah, that's actually a great question. Sure, you want me to elaborate on this?
Yes. Yes.
Okay, okay. So this is slightly Python specific, and yeah, I'm glad you asked this. So if you noticed a lot of things in this class, right? Some of you must be wondering, how come when I just call this net with, and net is basically the network object, I just call this this is basically equivalent to this call method, right? Whenever you call a object straight away with some curly brackets, it means you're invoking the call method with this input, and it gives you the output. So this is running the forward method. So you must be thinking, so who is telling this class that the call method should be overridden by this forward method, right?
Yes.
This and more other stuff is what is taken care of by this NN module superclass. Hence, we inherit from this NN module superclass our class, right? And before we initialize our model, we initialize all the aspects of the superclass so that all of such details are sorted already. We don't have to reinvent the wheel all the time. Otherwise, I should be calling, the true way of doing this should have been like this. But I didn't need to do that, because that is taken care of by the standardizations that is carried on by the NN dot module. This is basically, it is giving us the standard package that is required for neural network kind of objects to function. Once again, this is a brief explanation. You can just Google NN dot module torch and you will just see the full explanation. You can even go and check how this class looks like. It's not too difficult to understand, but great question. No one usually asks such a nuanced thing, but that's the reason behind it, to standardize everything. All right, Ritu, I think with that,
Yes.
we conclude this session. If there are
Yes.
questions, You can throw them at me.
I
I'll
can
try to
filter
answer it.
those questions and I'll share it with you. And we can continue those questions for like 10 minutes before we start the session tomorrow. And then we'll.
For sure. Yeah, let's do
Yeah.
that. Let's do that.
Cool.
Yeah.
Okay, great, Ashish. Thanks for the wonderful session.
All right.
And we got some great suggestions from our, alumni.